Okay, so now this is the third section of our class, the final class of our semester. Then in the first section, we have finished converting the integral Gauss's law into the differential formulation. Now we'll proceed to convert the other two of the Maxwell equation, the third and the fourth one. They are related to the line integral of the electric field and magnetic field respectively. And therefore, the question we will ask and think about is that could we write the line integral in a differential formulation? Well, let's start with the easier one, which is the third equation, which says the line integral of the electric field is equal to 0. I have to emphasize it is along the closed path or a loop. Sometimes we call it a loop because it's a圈圈. Okay, so usually we put a circle on the integral sign to emphasize it's a loop. Remember, the electric field satisfies that it has an electric potential. We can define a function V in the space. The difference of electric field is equal to the line integral between the starting point and end point. We have already discussed this last week. If you apply this formula to a closed loop, by closed loop I mean when this path, the end point and the starting point are the same, then this path becomes a loop. When it becomes a loop, the delta V, because the starting point, the delta V is the difference of electric field between the starting point and the end point. So if the starting point and the end points are the same points, then delta V must vanish, must equal to 0. Therefore, it tells you that the line integral of electric field along any closed path is equal to 0. So it is a profound, profound physical law. It tells you any of the electric field you can produce in space must satisfy this very, very stringent formula. Okay. Now, we would like to convert this integral law into a differential form. And the key observation is very, very similar to what we use in Gauss's law. Here, we face a curved space and its boundary. Now, I would like to say that if the curved space can be divided into two regions, A plus B, like in the following diagram, then the boundary gamma of the original space would be divided into gamma A and gamma B. These two subpaths actually has a interface in between. We call it gamma AB. So if we do the line integral along gamma A and gamma B respectively and add them up together, you will see very clearly the contribution from the interface gamma AB will cancel each other. The reason is simple. Because on gamma AB, path gamma A and gamma B actually move in opposite direction. I can show you from the following diagram. For gamma A, it follows this arrow, and when it reaches gamma AB, the interface, it moves in this direction as the mouse shows. However, if you look from the region B, it flows like this. And there it flows like this so that it becomes a smooth motion around the whole path of gamma. And if it moves like this, then in between, it actually on gamma AB, it moves in the opposite direction from the direction we move, looking from region A. Okay, so this direction is opposite to this direction. However, the vector field, for example, the electric field you are going to integrate over is identical on the path. Therefore, the integral must be negative to each other because the ds will be different. Therefore, when we add the integral from gamma A and gamma B, then the contribution from gamma AB will cancel each other. What remains will definitely be the outside, the outer path, and the other outer path. Okay, so when you add up the integral on the outer path, it just equals the line integral of the path gamma. Okay, so that means you can decompose a path into two subpaths, and their line integral will add accordingly. Therefore, with this theorem in mind, I can easily just decompose any loop or any closed path into small square like this. Okay, and therefore, for the same reason, for all those interior paths will cancel each other from the line integral on the right and the line integral on the left. The contribution will cancel each other for the same reason as I have outlined in the earlier transparency. Okay, so let me say any path can be decomposed into the combination of a series of small squares, and the line integral along gamma will be equal to the sum of the line integral along all the small squares. As I say here, the I is the electric field on the I square. ds is the path or the edge of this small square, and then you do the line integral on this small square and add them up. It will be equal to the line integral across the whole loop. Again, because all the overlapping paths, the contribution for all the overlapping paths, the contribution will cancel each other. It's a very useful observation we'll use in the next couple of transparency. But first, I would like to calculate the line integral along this square. And so let's consider a very small square on the xy plane. So this is on the x-axis, y-axis, and there's a very small square. The edge length will be delta x and delta y. So there is a path on the boundary of it. From here to here, we call it section 1, section 2, section 3, and section 4. Then I will calculate, and on this diagram, the electric field is called C. Okay, so that's imagine this C is the electric field. Anyway, so on this diagram, I calculate the line integral of electric field along every section, every path. For section 2, because it is moving along the y-axis, therefore it will pick out, because it is the inner product of ds and E. Therefore, it will pick out the y component of electric field along the second section. And the length of the delta, and because this square is very small, we assume that this EY2 is a constant along the path. Okay, therefore, we don't need to do any integral. We just multiply the approximate value of this y component of electric field with the length of the path. The length of the path, we call it delta y. So it's EY on the second section dot delta y. Then section 3, we assume that it is along the negative x-axis. Therefore, it will pick out the minus EX component of electric field along the third path. Here I say it's on 3. And then there will be delta X, that's the length of the edge, okay, of the subpath. So this contribution on the third section will be this. Then the contribution from the first path, the contribution from the fourth path. If I add them up together and collect the contribution proportional to delta y in the first term, and those proportional to delta x in the second term, the expression could be written in this way. Okay, and take out the delta y, and we see that here I can take out the delta y, so the first term is proportional to ey on the second path minus ey on the fourth path. Remember, ey2 on the second path is here. It is located when x is equal to x plus delta x, as I have shown here. And ey4 is located on this path. It is located with the x coordinates equal to x. Therefore, there is a difference between the x coordinates of the first term and the second term. According to calculus, the difference of ey, if you look at ey, if you're looking at ey as a function, then the difference between the function will be equal to the derivative times the variable change delta x. So it will be equal to dey over dx. However, here, because it is a multivariable function, in doing this derivative, I keep the y-x coordinates fixed. Therefore, this derivative is actually a partial differentiation, or we call partial derivative. So it is ey taking a partial derivative with respect to x times delta x, which will give you the first term, and then it times delta y. It becomes this, partial ey, partial x times delta x. That accounts for the difference of the function times delta y that exists in the original expression. Okay, so we finished calculating the first term. The second term, it could be dealt with likewise. However, here, the 3 and 1, the third and the first section located here and here, they are separated by a delta y. Therefore, this ex should be taken, we should take the partial derivative of ex over partial y. Okay, and times delta y, that would be the difference between the two functions. Oh, this should be a negative sign, okay, a typo. And so partial ex, partial y times delta y times the delta x originally in the expression. We got the second term. So please notice that in both terms, there is a delta x, delta y. We can take it out, so the expression can be simplified into this form. Partial ey over partial x minus partial ex over partial y together times delta x, delta y. Now it's obvious delta x, delta y is the surface area of this small square. We call it delta A. Okay, and the term in front is actually the z component of the curl. I write it here so that you can recognize it. Okay, so this is the z component of the curl of E times the area. Remember, for this area, if we follow the same convention, that give the area a direction normal to it. In this case, this area of square lies on the xy plane, so the direction normal to it is the z direction. Okay, so this expression just equals the curl of E as a vector, taking the inner product with delta A vector. Let me emphasize again, delta A is along the z direction. So when you take an inner product with curl E, it pick out the z component of curl E. Okay, so we finished converting our calculation into a very beautiful vectorial form with a differentiation. So it tells you the line integral along a small square on xy plane is equal to the curl dot delta A. Okay, however, on the right hand side, we write this expression in the vector form. Therefore, we believe this expression is not only true for a small square on xy plane, because on the right hand side we don't see any trace that it is on the xy plane or the delta a's along the z direction. Okay, so therefore we believe this expression is true for any small square on any plane. Okay, so so we finished finding the line integral along a small square which is equal to the curl times the area. So therefore, sometimes we will call the line integral we will call the curl of a vector field the line integral per unit area, just like in Gauss's law, we will say the divergence equals the flux per unit volume. Here we would say curl E is just the line integral per unit area. Okay, so it's a very beautiful calculation, and we can use it now to calculate the line integral along any path. So again, from the earlier page, the last page, the line integral along a small square equals the curl times the area in taking inner product. And we have also shown earlier the line integral along any path. For example, on this diagram, here where I have a loop gamma, and I divide it into small squares. Then the line integral along gamma will be equal to, as I have shown last page, it will be equal to the line integral along every small path, every small square, and sum up together. Okay, so we got a sum up of I, and EI dot DSI is the line integral along the ith square. Okay, but now I know how to calculate this integral for a small square. It is equal to the curl of E at the ith square dot delta AI. And this is just and sum up and then sum up over I. This is just exactly the expression when we take the limit, the delta A approaching 0 and the number of square approaching infinity. This expression will approach the surface integral of curl E. Just check the expression with the electric flux. It is the same. Okay, so therefore the left hand side approaching the curl of the surface integral of the curl through this curved surface with gamma as its boundary. Okay, so I hope you get the logic here. Maybe I could write down the final formula so that you can better understand the logic here. Here I have a curved surface, we call it S. And then there is a boundary, we call it gamma. Mathematicians like to write this in this expression. Gamma is equal to del S. And this del S means the boundary of the surface S. Okay, so if you take the electric line integral of the electric field along the boundary, we call it gamma here. The theorem we have just outlined will tell you it is equal to the curl of the electric field through the surface S. So it is the surface integral of curl E through the surface S. So this theorem is so important. We call it, there is a name to memorize the original inventor. It is called the Stokes Theorem. Okay, so when people say Stokes Theorem, you better understand it is just the mathematical theorem that connects the line integral of the electric field to the curl of it. Okay, well, even though I need to emphasize two things. First, even though here I say it is electric field and use the notation throughout all the outlines, however, you can see very clearly we haven't used any special property of electric field. So this E could be any vector field. Okay, you can think of this E just as the notation for any vector field. It could be B, it could be any other vector field in the space. Okay, of course, I will use the E first. Okay, secondly, in the proof, it seems that we decompose this loop into small flat square. So you may be under the impression that this loop must be on a plane, a flat plane. However, mathematician has been able to prove that this surface does not need to be a flat plane. It could be any curved space. For example, on the left-hand side, we have a very, very curved surface. On the right-hand side is the same. The surface could be it's bulked up. So the surface could be any curved surface as long as it has a closed boundary. Then I can apply this Stokes theorem to it. Again, with the boundary in this page, the boundary is called C, and it's the boundary of this curved surface. Then if I take the line integral, on the right hand side, the line integral of any vector field, here I call it F. I take any line integral of F along the boundary C, it will be equal to the curl of F doing a surface integral through the surface S. Okay, so again, it's an example where we can connect the quantity. Here it's an integration on the boundary to quantities in the middle. So again, it's very similar to Gauss's theorem. So in advanced mathematics, actually the two theorem can be combined into just one theory, into one theorem. Okay, so they in other words, it's only two aspects of one single theorem. Okay, so if you have maybe you will meet, if you are doing more theoretical physics, you will probably be able to meet this kind of derivation in the future. Okay, but I'll leave it here. So just that you can see there are some similarity between Stokes theorem and Gauss's theorem. However, remember, Stokes theorem is about the line integral and curl. The Gauss theorem is about surface integral and divergence. Okay, so now we finished the mathematics, over to the physics. The physics is quite simple. Here, the integral formulation of the third Maxwell equation, the line integral of electric field along a small path, a closed path, always equal to 0. Now I apply this law to a small square. Of course, small square is a closed loop, so it could apply to a small square. And then let the size of the small square approaches 0. But we have already derived for a small square, the line integral is just the curl dot delta A. Therefore, if the line integral is always 0, that means that the curl E must be always 0, because you can choose this small square at any place in the space, and then it will tell you that the line integral is always 0 everywhere. Then it will tell you that the curl of E is 0 at any point of the space. So we got the differential formulation of this Maxwell equation. Okay, and then how about the reverse side? We did it for Gauss's law. So let's start with the differential formulation with the curl E is always equal to 0. Now I plug it into the Stokes theorem. Stokes theorem again, line integral equals to curl surface integral. If you plug it in curl E always equal to 0, then the right hand side is always equal to 0. That means it gives you the line integral of electric field is always 0. That's the integral formulation. Okay, so on a single page, I derive the differential formulation from the integral formulation, and then derive the integral formulation from the differential formulation. That means the two formulations are equivalent to each other, here and here. Okay. So if this is possible, how about Ampere's law? Ampere's law is also about the line integral. So it is a line integral of magnetic field along a closed path. Along a closed path, then you do the line integral, it will be equal to mu 0 times I. I is the current flowing through the loop, like this. Now, I have to prove that in order to convert this expression into a differential form, I would like to convert to the right-hand side first instead of left. The right-hand side, the I, the current. The current actually could be written in the more concrete way by the current density, because we know that the current is the charge passing through a section per unit time. Therefore, the larger the area, the larger the I. Therefore, I can derive the current with the area of the section. Therefore, then the quantity we get will be called the current density. Okay, so remember this identity. J is equal to IA, or on the other hand, I is equal to JA. Okay, the point of using J is very, very simple. With A taken out of I, then this J is independent of the section. So I can define this J at any place in the surface, in the space. For example, if you have a current like a 土石流 in this diagram, okay, then it means that the direction of charge moving is could be very different at different places in space, unlike in a conductor wire. So if the current flow like this, that means the J will be different at different places. Okay, so I can give the current direction, I can give the direction of the charge moving as the direction of the charge of the current density J. Okay, therefore J is elevated into a vector. Also, because I can do the same thing at various points in space, therefore this J is also a field. It's a vector field. Okay, so and it could be proven that this J vector is actually equal to the density of charge times the velocity or speed, the velocity vector of the charge moving. Okay, and with this J defined as I over A, I can reverse the formula, pulling this A to the left-hand side and get I is equal to JA. Even better, if this formula is only true if the plane is perpendicular to the direction of current moving, the charge moving, or J. However, if the area, so if I choose a surface, then I will be equal to JA. On the other hand, if this area is not perpendicular to J, we can still project this area into an area perpendicular to J with A times cosine theta. And then all the current flowing through this perpendicular surface will also flow through this area A. Therefore, the current flowing through A is equal to the J vector taking inner product with A vector, J dot A. From this formula, you can easily see this is just the flux, just like electric flux. It is the inner product of electric field and the area. Here, the I is the inner product of charge density and A. So using the same, so there's a similarity between the two formalism. And therefore, in order to calculate the current flowing through a certain curved surface, I can always use this formula. I can always cut this curved surface into small pieces of flat plane. On the flat plane, the current flow through it could be easily calculated as J dot dA, just like we have done in calculating the electric flux. And then sum them up together and taking the limit dA is approaching 0, it becomes an integral, or put it most precisely, it is a surface integral. So this formula is actually very useful. The current flowing through a curved surface is equal to J dot dA, the surface integral of the charge density, the current density. Okay, with this formula in mind, it is so easy to convert the Ampere's law into differential form, because in Ampere's law, the line integral of electromagnetic field equals mu 0 I. This I is just the current flowing through the surface inside the path, the boundary, okay? And according to the formula I have just shown you, this I could be written as a surface integral of the current density, J dot dA, taking a surface integral. We also know from Stokes' law, the line integral of magnetic field equals to the curl dot dA. Therefore, this line integral could be written both as the surface integral of J and the surface integral of curl. Combining that to each other, that means this J must be equal to the curl B. Okay, therefore, I arrive at the differential formulation of Ampere's law. The curl B is equal to mu 0 J. Okay, so of course, now I derive the differential formulation of Ampere's law from the integration formulation. And actually, you can do the reverse yourself. So we understand that the differential formulation and the integral formulation are equivalent to each other. So let's put everything together. Now I have the differential form for static fields in Maxwell equation. Everything is here, okay? So let me just summarize a little bit. So the line integral of electric field equal to 0, that translates into the curl of E equal to 0. Line integral of magnetic field is equal to mu 0 times I, the current. The I current could be written as a surface integral of charge current density. Therefore, the fourth equation can be converted into the curl B equal to mu 0 charge current density. Okay. Please observe that, therefore, the Maxwell equation is converted into four equations about the curl and divergence of the electric field and magnetic field. Okay, so the structure is so simple. Okay, so now, but this is only for static field. How about the changing field by induction? If the magnetic field change, then it will generate an electric field by induction. We call it Faraday's law, which is known almost by everybody, okay? So the law is like this, Faraday's law, the line integral of electric field is no longer equal to 0 if there is a changing magnetic field. But Faraday told us it is equal to minus phi b over dt, the magnetic flux. And the magnetic flux is defined as the surface integral of magnetic field. Okay, and in this formula, on the right-hand side, only the magnetic field will change with time. The dA does not change with time. Therefore, the right-hand side could be written as the magnetic field taking a derivative with T dot dA. Remember, the Stokes law tells you the same line integral of electric field equals the curl of E dot dA, the surface integral. compare to the two expression, you immediately understand curl E is equal to minus B taking a time derivative of it. Okay, so that's the third equation with changing electromagnetic field. Okay, so this term B taking partial B partial T comes from the famous Ferris law, the changing magnetic flux. And after your general physics class, you also know that there's a very, very similar term on the right-hand side of Ampere's law in addition to the current, which is the phi E over dt. Therefore, you just compare the two expressions. I think I will not go into the derivation again, but you can easily derive that on the right-hand side of the curl B, there will be an additional term, which is the partial E, partial T. We are done. So that's the complete Maxwell equation in differential form. But let me emphasize the two terms that appears here are very, very important because they are the effects that the changing magnetic field and the changing electric field will generate electric field and magnetic field. So you can easily imagine we exist in vacuum. In vacuum, there is no rho, there is no J without charge, without current. However, there is a possibility that the changing magnetic field will generate electric field, and the changing electric field will generate magnetic field in turn. Okay, so therefore, the Maxwell equation in this form actually provides you with a mechanism that could generate each other, electric generate magnetic, magnetic generate electric in vacuum without anything. So that's the beauty of these two terms we just add. Actually, that will be the topic of our fourth section. I will derive the wave equation directly from the Maxwell equation in vacuum. Okay, so let's have a break, and we will have a very brief fourth section. You will see that actually this derivation is very, very simple and very, very easy. Okay, let's have a break.